explain optional project 1B. Yeah, I call it 1B, okay? 1 is our regular project, but 1B, the optional, okay? Let me turn off the light. Yeah. The problem is interesting. For other students, even if you do not plan to do it, yeah, because you can learn something. Yeah. All right. Yeah. So let me explain the main idea, okay? All right. Okay, all right. Yeah. First, what's the goal? First, let me give you the objective of this optional project, okay? Objective. You can think about it. So this is a problem solving. You need to solve a problem, special problem. Okay, that's objective. Did I? Oh, I didn't change the color. All right. Yeah. So the objective of this optional project. Yeah. Okay. Yeah. Find the minimum number of multiplications for the monomials x to the nth. Given x value, you need to calculate x to the nth with the minimum number of multiplications. Okay? Yeah. What we have learned so far, we have two special algorithms that give us close to optimal, but may not be exact optimal, right? Close to optimal, but not optimal. Yeah. So here, actually our goal, we want to find an optimal algorithm. Optimal, okay? Yeah. All right. Yeah. So here, let me explain the main idea. So that's the problem, okay? The problem. So the main approach we will do, we use the bottom-up dynamic programming. So we want to practice that a little bit, the idea. Yeah, let me describe what's the bottom-up dynamic programming, okay? So here we use the main method we use the bottom-up dynamic programming. Okay, all right, so this technique, okay? How to do it? How to do it? All right. Dynamic programming, the idea, we build table, right? So we build our data. Yeah. So that's the idea of dynamic. People also call it dictionary method. We build our dictionary. So the dictionary store our intermediate data. Intermediate data. Okay? All right. So here, so let's build our table, our dictionary. Okay? Yeah. All right. First, let's study let's work on the base cases. Because when you build from bottom, we need to start from the base cases. Okay? Yeah. First, we start from the base cases. Okay? Yeah. Base cases, you know, when n equals 0, no multiplication, right? Yeah. Oh, yeah, let's start from x to the first. X to the first, 0 multiplication, right? Yeah. X squared, 1 multiplication, okay? All right. X cubed, 2 multiplications, right? X to the fourth, 2 multiplications. X to the fifth, 3 multiplications, okay? Although we may not need that many, yeah, but so let's just, when we start our dictionary, the base level, yeah, so we can fill in the simple data easily, okay? Then, higher level, we do iterations. So we do, you know, the recursion, but bottom up, you know, going up. Yeah. Like a Fibonacci numbers, we calculate from bottom up, okay? Yeah. Not top down, from bottom up. Yeah. All right. Then, when we do that, our iteration, yeah, we need to use repeated squaring and repeated cubing. We need to use the, you know, these two methods. But when we use them, we try to use best of the two. Because sometimes repeat squaring does better. Sometimes repeated cubing does better, right? Yeah. So our idea is when the repeated squaring is better, we take the repeated squaring. When repeat cubing better, we take the repeated cubing. That's our idea. Okay, we mix them. Okay, we mix them. Mix in a, you know, well organized way. All right. So here, before I run that, let me first recall repeated squaring, repeated cubing a little bit. It's simple, yeah. But let me, for all students, I just write here. Okay, the pseudocode, simple, so simple. Yeah. Many of you implemented. Yeah. So here, all right. I do this. Okay. All right. Yeah. First, repeated squaring. I use this. I define function repeated squaring and function. Okay. Yeah. So this function. So yeah, we do like this. Yeah. If n mod 2 equals 0, yeah. So then, recursion, yeah. So this number equals, yeah, so here I just, yeah. So the number multiplication, RPS plus 1, right? Yeah. Yeah. So we split. So that number in half, but we square it. So this plus 1 multiplication for the square operation. Okay? Yeah. So we calculate x to, you know, x to n over 2, then square. Okay? The square. So plus 1 more multiplication for that square. Okay? All right. Then, and if equals 1, all right, then RPS, that number, plus 2, right? Plus 2. Okay? Why plus 2? Because you have one more x times that square. Okay? Square you have 1, but another extra x, another multiplication. So plus 2. Okay? All right. Similarly, for repeated cubing, RPC, repeated cubing, we have the similar implementation. Okay? If n mod 3 equals 0, so that number should be RPC n over 3 plus 2, right? Yeah, because cube, okay? Cube. So we need 2 more multiplication. Cube, you need 2 more, okay? All right. And another thing is, yeah, actually, because if you do the mod, you have 2 cases, right? Yeah. Here, actually, we can combine 2 cases. We can combine 2 cases, not equal to 0. 1 and 2, 1 and 2, yeah, yeah. Actually, the number the same, yeah, yeah, yeah. Although the multiplication could be different, yeah. So, RPC plus 3. 1 more. Okay, 1 more. Yeah, yeah. So why 1 and 2 the same? Yeah. So 1, you use x, you multiply cube, you need 1 more, right? But the 2, can you see why 2 we also need just 1 more? Can you see that? 2, we still need 1 more, but not 2 more. Because can you imagine x squared when we calculate this x, other, we need to have x squared, right? Yeah? We just save the x squared, okay? We do not recalculate it. We use the existing x squared value, okay? So in that way, 3 more. So that's repeated squaring, repeat cubing, so available. Okay, all right. Next, we write our optimal function. We define our optimal function. Okay, yeah, yeah. All right. This time, yeah, we want to define optimal function, okay? Yeah. We need to call, yeah, in this one, we need to call repeated squaring and repeated cubing, okay? All right, yeah. First one. We try repeated squaring, okay? If okay? Yeah. Yeah. How about this? Yeah. Because, all right, if n mod 2, mod 3, that's the detail inside repeated squaring and cubing, right? So outside, so we do not need to worry about that, right? Okay, so let's do this. Okay, all right. This optimal, first we calculate, we create a variable. Temporary variable A equals repeated temp A. Yeah, we store. So first we evaluate repeated squaring and see what do we get. Okay, all right. Second, temp B, repeat cubing. Okay? Yeah. Which one's smaller, which one larger, we don't know. Okay? How about we define op n equals the minimum How about that? Okay? Minimum. Okay? Yeah. Yeah. And going up. Okay? From bottom going up. Then you can see sometimes we use repeat squaring, sometimes cubing, you know. We try to find the best way, you know. How about that? Okay? To give you better impression, let me run some experiments. Okay? Here, I just run experiments up to 10. How about that? Yeah. We don't have to do too many. Up to n equals 10. Okay? All right. So when we start, our base level 5, then we go another 5. Okay? So the base level, first, that's 0. Square, that's 1 multiplication. Cube, that's 2 multiplication. 4, also 2. X5, 3. Okay? So that's our base level. Now, let's do n equals 6. N equals 6. So temp A, what's temp A? Temp A, because 6 mod 2, remainder 0, so it should be, half, right? Half the number 2, 2 plus 1, okay? So equals 2 plus 1 equals 3. Okay? Temp B. Yeah. Temp B also mod 0, so x2, that's 1. 1 plus 2. Okay? 1 plus 2. Also is 3. Okay? 1 plus 2. So that tells us OPM 6 equals 3, minimum. Okay? Yeah. N equals 7. Temp A. Yeah. Temp A. Mod 2, 1, okay? 1. So that's 1 half. 1 half 3, right? 3, 2, 2 plus 2. 2 plus 2 equals 3. Okay? Temp B. Mod 3, 1, yeah, but divided by 3, 2. X squared, that's 1. 1 plus 3 equals 4. Okay. Equals 4, we take the smaller one. OPM 7 equals 3, not 4. Question? Oh, yeah, oh, sorry. You're right. Yeah, 2 plus 2, 4. So it should be 4. Yeah, not 3. Yeah. Thank you for correcting me. Yeah. All right, good. Then n equals 8. Temp A, 1 half 4. 4 is 2. 2 plus 1. Yeah, this time 2 plus 1 equals 3. Temp B, mod 3, 2, remainder 2. 2 divided by 3, 2. So 2, that's 1. 1 plus 3 equals 4. The smaller one is 3. OPM 8 equals 3. Okay? 2 more to go, 9 and 10. Okay? So you get the idea. Equals 9. Temp A, mod 2, 1, divided by 2, 4, x to the, that's 2. 2 plus 2 equals 4. Okay? Temp B mod 3, 0, remainder. So divided by 3. So 3 is 2. 2 plus 2, also 4. So OPM 9 equals 4. Okay, the last one 10. Okay, yeah. So there, I think everyone can do it. Okay, mod 2, 0, remainder. So temp A equals 5. Okay, 3. Yeah, x to the 5th. 3 plus 1, 4. Yeah. Temp B, yeah, mod 3, 1. So divided by 2. 2 plus 3, okay, 5. Then the optimal should be 4, okay, 10 should be 4, and so on. How about that? Okay. That's what we call the bottom-up dynamic program. Bottom-up, okay, yeah. A typical bottom-up, yeah, yeah, yeah. Here, you may, yeah, yeah. Here, because when I use this RPS, RPC, yeah, actually, yeah, we may need to modify a little bit, right? Yeah, actually, yeah, because it may not be exactly RPC, RPS, right? Yeah. So you can imagine, yeah, I don't know. So how do we, although we use that RPS, RPC idea, because the values actually we updated, right? Yeah, so, yeah. So here, there is some little adjustment you may need to do. Yeah. So, I mean, how do we call these two methods? Some small adjustment you may need to think of. Yeah. Yeah. Other than that, you know, implementation is like this. Okay. Yeah. All right. So here, let me tell you. Yeah. The final, you know, how much it's worth. Okay. Yeah. This one, after you run, if you write a function like this, you implement, you run. Given n, you can generate. Yeah, remember I asked you to produce the optimal multiplication number from 100 to 200. Okay. Yeah. 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 Not too many. Okay. Yeah. Print out to see. Yeah. So print out. I like you print out. Repeated squaring, how many? From 100 to 100. So each one, okay? How many multiplication? Repeated cubing, how many? Then our optimal, okay? Our mixed optimal one, okay? How many? Okay? 100, 200, yeah. Print that number, yeah. Yeah, but if you only print a number, you can get a 2% extra credit, okay? 2% overall. Yeah. Then one more, if another 1%. For what? Because other than the number, you want to show how to do the multiplication, right? If you can keep track of. So each time when you select an optimal, you can keep track of how do you do the multiplication, right? Yeah, repeated squaring, so you have a special way. Can you organize your information, keep track of the way you do the multiplication? Then you will get another 1%. Because you need to do some work. You need to do some non-trivial work. Okay? So 2% plus another 1%. If you want to do a little more, total 3%. 3% of the whole class 100%. So 3 above that. That extra credit. Okay? Yeah. So if you want to try, if you feel fun, yeah, some students, so you feel interesting, so then you can try. Okay? Yeah, yeah. But last sentence, okay, last thing, before we move to the next topic. Last thing. Yeah. Yeah. Although here we try to do the optimal way, yeah, but the way we are doing here, we cannot prove it's optimal, okay? We just know it's better than repeated squaring, repeated cubing, and it is close to optimal, yeah. But it is hard to rigorously show it is optimal. Yeah, it's hard. I cannot prove it. Yeah. Yeah, rigorous proof could be hard. Yeah. So that's the one thing. So in your mind, you need to realize that. Yeah. Okay. Yeah. All right. Yeah. So that's the because several students asked me this one several times. So I have to give you this details. Yeah. All right. Yeah. So then let's move to our last part of Module C, Quicksort. Yeah. Yeah. Today we cannot finish. Yeah. So today we just do the first half. Yeah. All right. D.1, Introduction to Quicksort. All right. First, this Quicksort, because for each new sorting algorithm, you need to ask yourselves why we need to do another sorting algorithm, right? We already have so many. Yeah. Why we need to do another one? Yeah. This one has an important property. Yeah. Here it has probably the best overall performance. Yeah. Yeah, probably best because it's hard to say, the best. Close to best. Yeah, close to best. Yeah, yeah, because by experiments. So here, best or not the best. How do you prove it? Yeah, do experiments. Okay, people do experiments. Yeah. Run sorting on large number of data sets. Then do statistics. Yeah. Quicksort does better than other known algorithms. Okay? Yeah. But it's hard to claim it's the best. Okay? Yeah. Yeah. All right. Yeah. So we want to have the close to best overall performance. That's the average case performance. Overall average. So it does not have the best worst case. The worst case, merge sort has better worst case than quicksort. Quicksort, the worst case still n squared. Big O of n squared. So that's not the best. Okay? Merge sort, worst case n log n. Better than quicksort. Okay? But the overall average, quicksort has much better average case efficiency than the merge sort. Yeah. All right. Use divide and conquer again. So this time. But we use divide and conquer in different way. Yeah. Different from merge sort. Yeah. Here we do comparison with the merge sort. Okay? All right. The goal, make the overall performance as fast as possible. Yeah. Yeah. It's hard, but we try to use a different idea. Yeah. Tolerate poor worst case performance. Yeah. We allow merge sort, avoid poor worst case performance. Yeah. But here because it's a trade-off issue. Yeah. In order to get a better overall efficiency, we need to sacrifice a little bit. So this is our sacrifice. Yeah. So we tolerate some poor worst case efficiency. Yeah. But the probability for the worst case is very small. Yeah. Probability. Yeah. So it's not an issue. Yeah. So in the experiment, it's very hard to hit the worst case. Yeah, very hard to hit the worst case. Okay? Yeah. All right. Change view on divide and conquer. How do we apply the divide and conquer approach different from the merge sort? Yeah, let's do a chart. Okay? Yeah. Yeah, do this chart, do comparison. Okay. So for the merge sort, the divide step easy. We just cut right in the middle. So the divide step, big theta of 1, that cost. Very cheap. All right. The new idea, because new idea, you have to do some work, right? You have to do some meaningful work. So the new idea, we put our meaningful work at divide step. When we divide our array, we do a little more work. Conquer recursion. Nothing. Conquer, we just call the function recursively. So nothing special to do. Okay? Combine, merge, sort, we need to do a lot of work here. Combine two ordered arrays. But this new idea, when we combine, we want to do the minimum work. Minimum. We want to save at the combine step. The minimum work, we just put two ordered arrays together, we get a whole array ordered automatically. That's what we want to have for this new idea. Okay? Here you can see, so we, put our attention in different places. Here, okay? All right. So how to get this new algorithm? So, here, the divide and conquer, we will do completely different from the merge sort. All right. So here, current data size. All right. So that's the quicksort idea. Okay. All right. Next, we need to, make it work. Try to implement that idea. Make it work. Okay. All right. Almost do nothing in the combine step. What do you mean almost do nothing in the combine step, right? How do you set up, set the stage? How do you arrange your data? The ideal situation of your data. So two subarrays ordered after the conquer step, then you simply put these two ordered arrays together, like concatenation, the whole array is ordered automatically. You want to have that special situation to make it happen. You need to do the work. It's not free. That ideal situation, not free, you need to, pay. You need to pay. Okay? All right. Let's consider two subarrays. So here, we try to understand. We try to find the critical condition to make it work. Okay? There is some condition we need to have. All right. Consider these two subarrays. Okay? Divide and conquer. Before conquer, Before conquer, we split our data into two subarrays. Then after conquer, we sort them, right? Conquer means you call the function recursively. At the end, you sort it. That's the conquer step. Okay? So before conquer, not sorted. After conquer, each one is sorted. Okay? Each one is sorted. So now you want to combine them. Combine two ordered arrays. All right. But when you combine, you want the whole array is automatically sorted. You don't want to do extra work. If you do extra work, that means your divide step is missing something. You didn't do enough in your divide step. If you do enough work at your divide step, then your combine step, you do not need to do anything. Just put them together. You get it sorted. Okay? All right. So that means this merge step, the cost is minimum. Or you can say the cost is big theta of 1. Minimum. Okay? All right. The goal After conquer, when combine, do nothing. Yeah, do almost nothing. Yeah, just nothing. Okay? Yeah. All right. Nothing significant. Yeah. What condition do we need before the conquer? Yeah. Here we need to, backtrack. Yeah. Recall, go back to the situation before the conquer. Before the conquer, the data split should satisfy certain condition. Okay? Yeah, certain condition. Yeah. All right. Can you imagine some special condition? Yeah. So here, this condition. How about any element in A subarray is less than or equal to any element in B subarray? How about that? Or the maximum in A subarray is less than or equal to the minimum in B subarray. How about that? Okay? Yeah. Yeah. So if you have this condition, then when you combine, automatically sort it, right? Yeah. That's the special condition or requirement we need for the divide step. For the divide step. Okay? Yeah. All right. Yeah. It's not easy, yeah, but this property is important. We need this property. Okay? Yeah. So we are willing to pay a little more at the divide step to get this property. Okay? All right. Most important step for Quicksort, divide step. Because that's the place we pay by number of comparisons. Pay the most by number of comparisons. Okay? All right. Requirement. How to split the array into two subarrays, A subarray and a B subarray, such that A of I less than or equal to B of J. That is our main requirement for the divide step. If you can do this, then Quicksort almost there, right? Think about it. If you can make this step work, the whole Quicksort almost there. Okay? Yeah. You just do recursion, right? Yeah. Keep doing this. And the recursion, yeah. Okay, yeah. Quicksort is done. So next, we need to understand the detail of implementation of the divide step. Then we get the Quicksort. That's simple. Okay? All right. Let me look at the time. All right. All right. Yeah. So here, one little thing. We do not require that A subarray, B subarray are sorted at this point. Yeah. After divide step, you do not need that, right? Yeah. A subarray not necessarily ordered, B subarray not, and in general, they are not ordered. Yeah. So you call recursion, conquer, you make them ordered, sorted. Okay? Yeah. Conquer, recursion. So you make them ordered. Okay? Yeah. All right. D.2, next, partitioning in Quicksort. Now we need to, get all the details of the partition step. Okay? Yeah. All right. Yeah. All right. So that is the critical requirement when we do divide step. All right. Yeah. But we need to, so here, you need to use your analysis to figure out how to make it happen. Okay? Yeah. Implement the divide step. Fixing the implementation details. Here. The problem solving, the key step here. All right. Assume this is our original array. Yeah. Array elements. Yeah. Now, we want to divide it somewhere. All right. How to split? So the first step is hard. How to split it? Okay, yeah. And to get this condition, you need this requirement when you split into two subarrays. Yeah. Non-trivial. So here, you need to do some serious work. Okay? All right. Yeah. All right. To get that, there is an uncertainty regarding the sizes of A subarray, B subarray. You don't know how large is A subarray, right? And how large is B subarray? You don't know. Not like merge sort, we know the size of each subarray, right? Yeah. Approximately 1/2 of the original size. Here, you cannot assume that. Okay? A array, could be very small, could be very large, So we don't know. Uncertainty. Yeah. So in this problem solving, we need to find a way to handle that uncertainty. That uncertainty. Okay? Yeah. Non-trivial here. Okay? You need to find a smart idea to deal with that uncertainty. Yeah. All right, so let's look at that. What's that smart idea? How to make it certain. Make it certain, okay? The size of these two sizes, subarrays, make them certain. Yeah. All right. Yeah. A special element, yes. So here, this is the critical step, okay? Yeah. A special element to separate two subarrays. We rely on some special element to tell us where to separate these two subarrays. We need one element to separate two subarrays. Yeah, think about it. So here, suppose this is that special element. Okay? We want to select some element. It's very special, but this element separates A subarray and a B subarray to satisfy this condition. Let's imagine some special element has that special role. Okay? Has that magic role. Okay? Yeah. If we can find, so here, it's hard to find, but if we can find that special element, can you imagine what property that special element should have? If someone finds it, tell us, oh, this is the one. Can you see some critical property this special element must have? Look at this condition again. Look at that condition again. All right. Here, let me ask you, give you another hint. Think about the position of this element. Is there anything special about the position of that element? Random. If a random position, sort of random, but sort of random, but if random condition, element position, we want that element separate two subarray. Yes, that's the key property. In place. That special element must be in place. That's important, right? Yeah. If it's in place, in place. Never move. That's the final location where the whole array is sorted. Okay, in place. And at the same time, left subarray less than or equal to this element. The right subarray, all the elements should be greater or equal to this, the value of this element. In place. Okay? All right, so now you understand better, yeah, because that special element should be in place. But the question is, how do you find an element that is in place, right? It's possible that no element is in place, right? Yeah. So the next question is, how do we make this happen? Yeah. Yeah. Although we cannot find an element that is already in place, but can we make it in place? We want to make that element in place, right? We put an element in place. Then that element separates two subarrays with this condition. That's what we need. Okay? All right. Yeah. Yeah. So our next step, we want to fix the remaining details. Yeah. So you can see that, the idea is so smart. Yeah. All right. The key property in place. This special element. Determine the boundary of the two subarrays. Now, yeah, this element is the boundary, yeah, between two subarrays. Okay, but we need to determine, okay, this element, special element. Yeah. Here, we call it P. Yeah. P refers to the pivot element. We can give it a special name, pivot element. Okay. But the question is, how do we choose the pivot element, right? Yeah. You need to choose the pivot element. Okay? So the next question, how do you choose the pivot element? Yeah. Okay? All right. Yeah. And we know the meaning of the pivot element, the left subarray, all elements in the left subarray should be less than or equal to P, and the elements of all the right subarray should be greater or equal to that P value. P value, okay? That's the meaning of this pivot element. Okay, all right. Now, which element is used as the pivot element? Yeah. Yeah. So we try to get more and more details. Yeah. Next one, how do we choose a pivot element in a fair way, right? Yeah. Because you want to do it in a fair way. Which element to be chosen to be fair for a pivot element? Median? Do you want to say median? Anyone want to choose the median? Median as the pivot element? Yeah. Right. The median. It's not good to choose the median because the cost is too high to find the median. The cost. You need to find the median first. That cost is so high. Okay? So last time I give you some number, approximate number, about 16n. 16 times the number of elements in the array. So you don't want to pay that much cost. Okay? Too much. Yeah. So don't choose the median. Okay? All right. You would rather choose a random element. You would rather choose a random element because you have no idea on the values of the elements in the array, right? You have no information about the value distribution of the elements, right? Yeah. So the randomly selected element equally well, right? Yeah. All the elements, they have the equally, yes, yeah. You will choose no advantage, no disadvantage. Yeah. Okay, all right. Any element has an equal role in the array. Yeah. All right, yeah. No reason to favor any particular element, right? Yeah, no reason. Yeah. Because you do not have any information about the value. Okay? Yeah. So you have no reason to select one element over another element, right? You don't know which one is better, which one is worse. Okay? Yeah. All right. Could be random selection. So the pivot element could be a random selection. Okay? Yeah. So that's our understanding. All right, yeah. But when you look at the values, random selection, but how about position? We know all these elements, they have different positions, right? In this array, position, not equally good, right? Some positions better than other positions, okay? Some positions, more convenient than other positions. Yeah. Here we want to examine the position difference. Position-wise, element at which position is the most convenient for us, we programmers, to manipulate data. We need to manipulate elements, right? Yeah. So think about, for us, when we write a code, manipulate the elements, which position, if we use it to store the pivot element, that would be most convenient. Yes, good. All right. For other students, yeah, he already said that, the main point. For other students, let me, describe the story a little more. Okay. So what are those positions the most convenient here? All right. If we pick a random position somewhere in the middle, see what happened. Okay. Suppose we pick this position in the middle. So now we want to manipulate the elements. Yeah. This one, we put our pivot there, okay? Yeah. Because the pivot element, we'll randomly select one, and we put here, okay? Yeah, all right. Think about if we use this position, when we try to get A subarray, B subarray, we need to move elements around, right? From left to right, from right to left, okay? When you move elements from left-hand side of this one to the right-hand side, or from right-hand side to its left-hand side, what's the role of this element in the middle? It sits somewhere in the middle, okay? Yeah. It plays a role just as a roadblock, right? It blocks you, somewhere in the middle. You need to overcome it, right? When you move around, you need to overcome this position. So this position causes some problem for you, okay? Make you do more work, right? When you write a code, if you move around, you need to do more work. Yeah. Because this is a roadblock, okay? All right. You want to eliminate the roadblock, okay? Yeah. To eliminate the roadblock, the most convenient location, you want to use the first position and the last position. Only these two, that when you move elements, you do not need to touch the first position and the last position, right? Yeah. No touch, okay? No touch. You just move freely, right? Move without hitting anything, right? Yeah. Not like a roadblock sit in the middle, okay? Yeah. So you can see position-wise, there is huge difference. So we want to choose these two as the candidates. These two are the most convenient locations. So for the candidate locations of the pivot element. Okay. Yeah. All right. Yeah. All right. Yeah. These two, equally good. You can pick anyone. Okay. Yeah. All right. Yeah. All right. So here, let's pick the last one. Okay. Some implementation version pick the first one. Some pick the last one. Okay. Yeah. Equally good. Yeah. All right. So let's use the last position to store, to hold the pivot element. All right. Then we try to get an A subarray, B subarray. Yeah. So here you can see A subarray, B subarray are adjacent. Okay. Yeah. So, but we can move elements around. Okay. Yeah. Yeah. By swap operation, we can do swap operation to move elements, from into A subarray or into B subarray. Okay? Yeah. All right. Yeah. But we want to make sure all the elements in subarray must be less than or equal to P, and all elements in the right subarray should be greater or equal to P when we move elements around. Yeah. Like those two inequalities. Okay. All right. Now you can see we almost get all the details. Yeah. So this partition step, we almost get all the details. Yeah. So we just need to do some cleanup work. Okay. So we get all the pieces together. Okay. But we need to put everything together in a well-organized way. So next step, we need to organize our data in a convenient way. So then we can implement this partition step. All right, D.3, implementation in partitioning. Yeah. Oh, good, we still have 15 minutes. Yeah. So we can do this. I can show you the details of this implementation. Yeah. Yeah. All right, straightforward implementation. Yeah. First, when we start, let me just give you our first try. It may not be the best way, but get us started. Okay? Yeah. So we need to do something first. So straightforward implementation. How to split two subarrays? Let us use two auxiliary arrays to help us organize the data. Two auxiliary arrays. Later, we may like to eliminate these two auxiliary arrays. But first, we need help from these two auxiliary arrays. Yeah. All right. Yeah. All right, so now the setup. Okay, original array. Yeah. We pick the last element as our pivot element. Okay? You can just pick last element as the pivot. Another way, you select random element, some anywhere in the array, then you swap it to the last position. Yeah. That method is called a randomization. You do randomization of your data. Yeah. So that's some special way to improve slightly. Okay, randomization. Yeah. Here we just get a pivot element at the end. Yeah. All right. Now we scan the array from left to right, sequentially. Okay. All right. But in order to get the A subarray, B subarray satisfying the desired condition, yeah. So the two inequalities, conditions. All right. Yeah. The first inequality, second inequality. Yeah. Second here we just make it strictly greater than. Okay. Yeah. Yeah. Otherwise we have some uncertainty. Okay. All right. In order to get this kind of result, yeah. Now we use two auxiliary array. How about that? Yeah. This one, A, B subarray, two extra auxiliary arrays. Yeah. Then when we scan, let's look at each one. If it is less than or equal to P, we put it in A subarray. If we pick one, if its value greater or equal to P, greater than P, then we put it on B subarray. That's simple, right? So we scan once, okay? For every element, we either put it in A subarray or B subarray, okay? After we finish the scan, we have A subarray and a B subarray, okay? That's simple, yeah. But after that, we just copy the elements back to the original array. Copy back, okay? Then we can eliminate the two subarrays, release the space, right? After we use them, yeah, we don't need them anymore, we release the space. So we copy the elements back and release the space, memory space. Yeah. All right. So that's our first try. But in your first try, we use 2 auxiliary arrays. You need to use extra memory space, right? Yeah. We want to, in order to do better, we want to reduce our resource usage. Yeah. Can we eliminate these 2 auxiliary arrays? We do not use 2 auxiliary arrays. We just manipulate. We just swap elements in the original array. How about that? Without using auxiliaries, we can still change positions, right? Swapping, okay? Swapping. Doing swapping, we do not use auxiliary arrays. Then we save a lot of memory space. How about that idea? Okay? Yeah. So let's improve the improvement idea. Okay? Yeah. We don't use auxiliary. Yeah. A little challenging, yeah, but we can do it. We can do it. Okay? All right. Yeah. Yeah. I mean, space, too much space. Okay? So we don't like it. Okay? So we want to eliminate auxiliary. All right. Eliminate. When you talk about, yeah. So now we decide we do not use auxiliary. But when you manipulate elements, you may need a little extra space for your manipulation, right? Yeah. Yeah. So the extra space used, we need a little extra space, but we want to control to some limit. Yeah, not too much. Yeah. A little. Yeah. A little. Yeah. We can use a little extra space, but under control. Well under control. Okay? All right. So here. All right. Yeah. To do that, yeah, extra space. Yeah. So we leave some. So here, for example, we leave some, certain number of extra space. We can copy our temporary elements. Yeah. But not too many. Okay? Small number. Small number. Then people talk about big theta of 1 extra space. Yeah. Yeah. Big theta of 1. Yeah. So under control. Okay? Controlled by some constant. Yeah. Under control. Yeah. Then it's acceptable. Okay? Yeah. So then there is a terminology here. Terminology. The algorithm, if you implement an algorithm, the extra space used bounded by big theta of 1, such algorithm, we call it in-place algorithm. Okay? In-place algorithm. Here, another meaning of in-place. This time in-place, not for the elements in place. It's algorithm in place. Okay? Yeah, so here, we have a, in-place algorithm. Okay? Yeah. Those algorithms are desirable because you do not use too much memory space. Okay? You do not use too much memory space. Yeah. Yeah. The basic memory space you use, input, output. Yeah. Any algorithm, you have to store your data for input and output, right? Yeah. Other than input and output, then we call it extra space. Extra space means outside input and output. The extra space used bounded by big theta of 1, some constant. Constant. Extra space used. Okay? Those algorithms we call in-place algorithms. Yeah. The terminology here introduced. Okay? Yeah. All right. Then, now we want to use small number of extra spaces to help us manipulate elements within the original array. Yeah. Here, to organize that, yeah, the main issue, here, we are at the point we want to do another special work that's also very important in problem solving. That's the how do you organize your data? If you find a nice way to organize your data, then you can do it efficiently. Yeah. So another important point. Yeah. All right, so let's look. How do we organize our data? Yeah. So here I divide original array into 3 regions. S region. Yeah. S refers to, smaller. Okay. S region. Yeah. The elements in this S region smaller or equal to the pivot element. Larger, L region, larger. The elements in this region is larger than the pivot element. Okay? Then some elements in U region, the U region we refer to unprocessed. We haven't processed these elements, okay? Unprocessed. Yeah. So we divide all the elements other than P. P is special, okay? So we do not count P in any of the 3 regions. Yeah. Other than P must be in one of the 3 regions, yeah, for our implementation. Okay, all right. Yeah. Then, A subarray corresponds to S region. Okay, B subarray corresponds to the L region. Yeah. They are initially empty. Initially, no element, empty. We start, these 2 empty regions. Okay, all right. But we will grow. Okay, every time when we do comparison, we grow one of the 2 regions. Okay, all right. Then unprocessed region, initially, the whole array except the pivot element. Okay, the whole array except pivot element. Then shrinking. Yeah, so we shrink this U region. At the end, it's empty. It's empty, so we finish the processing. Okay, all right. Yeah, so with this preparation, so this is our mental preparation. Next, I show you the implementation details. Yeah. We only have 5 minutes. Yeah. I just run the example a little fast. So after 5 minutes, we can see how do we run the partition. Okay, all right. D.4, example for partitioning. Yeah. Here, I give you a concrete example. Yeah. Suppose we use this array. Okay? Yeah. To run it, I use animation to run it. And for different elements in the array, in different regions, I use different colors. So you can see clearly there are different rows. Yeah. The pivot, I use this color. Okay? This is pivot color of the, only one element. Yeah. Initially, all other elements in U region, so we use white color. Okay? Unprocessed, white color. Then S region, L region, 2 different colors. Okay? So let's run the comparison. Okay? All right. Extra space, we use 1 extra space to help us swap the elements. All right. Then let's run step by step here. Okay? When we start, S region empty, L region empty. We do first comparison. 2, compare it with pivot 4, it's less than 4, so we should put it in S region. Okay? Yeah. Comparison number 2, 8 and 4, 8 greater than 4, so we should place it in L region. Okay? Yeah. All right. Step 3, compare 7 and 4, 7 greater than 4, 7 also we add it in the L region, in sequence, okay, in their natural order. Yeah. Yeah. All right. Step 4, compare 1 with 4. 1 is less than 4, okay? So 1 should be in the S region, but if you look at the diagram here, 1 and 2 are separated by L region, the green elements. That's not good. We want to make the, all the elements in S region are adjacent each other. Okay? Yeah. Not separated. Yeah. So how to fix that problem? Swap. 1 swap operation, we can fix it. Okay? We swap element 8 and element 1. Element 8 and element 1, one swap, you get element 2, element 1, yellow color elements all in the same block. Okay? Yeah, back to back, same block. Yeah. Yeah. All right? Yeah. So one swap, you can fix it. Yeah. All right, continue. 3 and 4, 3, yeah, another swap. Okay? Yeah. Yeah. So in 2 regions. Yeah. All right. Number 6, compare 5 and 4, green region. Yeah. So now you finish the scan, right? Yeah. So you get a S region in yellow color, L region in green color, but the pivot element still not in place, right? How to put it in place? Another swap. The last swap, okay? You put the pivot element in place. You're done. Yeah. You complete partitioning, right? Smart, right? Without using auxiliary arrays, right? Yeah. Only limited extra space, okay? Yeah. So that's all you need to do, partitioning, okay? Yeah. So then, our Quicksort is there, okay? Yeah, you just keep doing this every time when you conquer a subarray, you apply this partitioning step, okay? All right, yeah, so we run out of time, so let's stop right here. Yeah. Next time there are 2 special cases, so we can finish quickly, okay? Next time, so we finish the whole module. Yeah. All right, yeah. So then this weekend, yeah, I may post, right. Yeah, actually, a lot of things. Yeah, quiz, homework assignment 2, and a new project I also need to post. And, optional, I need to, yeah, this week, a lot of things. Yeah, optional is optional, okay? Yeah, I separate it. The deadline, until the semester ends, okay? Yeah, until semester ends. Yeah. All right, yeah, that's it.